So, back to multirate DSP. All the tools that we have developed, we will now bring them back into the result that we are going to have. So, the first one, by the way, all of the material that we are doing for this section is from a book by author by name Yuan Pei Lin, and we will upload this chapter in Moodle. So, basically this is from the book of Yuan Pei Lin. So, I will use the notation YPL to refer to Yuan Pei Lin. In that book there is a theorem 4.1, and the theorem 4.1 is actually a result that we know. So, we do not actually have to call it as a theorem, but let us just write it down so that you will know when you read the notes where this one links in. So, we are basically going to look at chapter 4 and chapter 5 of Yuan Pei Lin. So, chapter 4 comma 5, this is in theorem 4.1. The theorem 4.1 in this book says a well known result to us, but let us pick it up with the notation. So, if I have an input x of n which I pass through an upsampler of by m, followed by a filter h of z, followed by a downsampler. Now, this you will be able to tell me what the answer is. So, if I call this as y1 of n, this as y of n, we know that this structure is equivalent to the following. This is actually an LTI system. We have derived this result or shown this result. This is x of n, this is E naught of z, the zeroth polyphase component of h of z, and the output will be y of n. This is actually an LTI system. Okay, so basically the theorem 4.1 says that this is an LTI system. This is an LTI system that is given by this expression. Okay, so the book also uses the following notation. So, when you read the book, so that you will there will be no confusion. It uses the following notation. Again, it's helpful for us. E naught of z is the zeroth polyphase component, is actually represented in this fashion: h of z downsampled by a factor of m. Okay, so what does this actually mean? If I write down the impulse response of h naught of z, this would be h naught plus h1 z inverse, h1 z inverse plus h2 z minus 2 and so on, and h m z power minus m dot dot dot. What we are doing with downsampling is keeping h naught, keeping h m, keeping h of 2 m z power minus 2 m dot dot. We are retaining these coefficients and we are writing it as a polynomial in z. So, basically E naught of z is h naught plus h m z minus 1, h 2 m z minus 2 and so on. Okay, that is E naught of z. There is a short compact notation for that. When you say that it is h of z actually represents a sequence and I am downsampling it. Okay. So, now can you see if we can just use this notation so that we can get comfortable with that. Okay, so basically what we have introduced is this block with a downsampling. Basically this is nothing but the downsampling that we are familiar with. Okay, so if I now go back to the original representation, we would say x of n passing through a downsampler. Downsampler is m. This would be y of n. This is equal to x of mn. This is the notation that we are used to. This is how we would represent the downsampling. Now, here is where if you wrote it in Z domain, this would have been 1 over m summation k equal to 0 to m minus 1 x of z power 1 over m w m k, and wherever there is a downsampler you have to write this equation, there is no way to get around it. Okay. Now, actually this is a cumbersome form, right, because you have to write the summation, there is all these powers of. Now, this is where it is very convenient to introduce a new notation. This notation is nothing but x of z downsampled by m. Very compactly you can write it down, and you will see in a moment why this is so useful for us, because this is very helpful for us. Okay. Now, as always, apply the result that you have just now obtained. Okay. Now, if I were to write down the expression for y of n, okay, y of n is y1 of n downsampled. So, let me see, let us see if we can write this expression. Okay. Y of z is equal to x has been upsampled, z raised to the power m followed by h of z, then downsampled, right. Under normal circumstances you would have the summation, all of those things coming up. Now, I am going to introduce the notation downsampled by a factor of m. Okay. Notice that if I have x of z power m downsampled by m, that means that is noble identity, it will become x of z. So, this can be simplified as x of z, and what is left is h of z downsampled by m. H of z downsampled by m will be E of z. Now, this is why we get an LTI system, because you can get y over y of z over x of z is equal to some LTI system, does not really matter for us, it is represented by this. Okay? Good, very good. So, this is LTI, and it is this notation actually comes in very handy in the analysis that we are going to be doing. So, hopefully you will see the advantage. So, let me ask a related question. Okay. Now, this is more of just an application of this. If I fed in x of n to h of z followed by a downsampler, okay, and this is y of n, I say, oh good, I already know how to analyze this. This would be y of z is equal to x of z h of z downsampled by m, because but I am not able to pull x of z out. So, this is not LTI, because when I downsample x of z, I will get the x of all the shifted versions. So, this is not LTI, because I cannot take out x of z. So, again this notation actually comes in a very handy and useful manner, but actually when you start using it, it actually becomes more beneficial. Okay. So, here is where we will now go back and build on the framework that we have developed. Okay. So, back to the reference figure, I will have to keep switching back and forth. This is my reference figure. Okay. Reference figure from here, this is the synthesis filters pass through the channel, passing through, I am ignoring the noise for the moment, passing through the analysis filters. Now, given the result that we have just now studied, can you tell me what is the transfer function between S naught of n and S naught hat of n? There is an upsampler followed by F naught, followed by channel C, followed by H naught, followed by downsampler. Okay. So, here is a, if you actually wrote down the equation, it is actually going to be quite messy, but if you now apply the result that we now have. Okay. So, basically I am looking at a specific transfer function from Sm of n, okay. That means it will go through Fm of z followed by an up, wait, it has to be first upsampled, sorry about that, I have to erase this. There is Sm of n upsampled by m or n, does not matter, we will just write it with n because that is what we eventually want to do. Then followed by the channel C of z, followed by h k of z, downsampled by n, and this one comes out to be Sk hat of n. Okay. So, mth input, kth output, that is the input output relationship that we are looking for. Now, if I call this transfer, this combination of these three filters as T k m of z, mth input, kth output, that is why I got T k comma m, T of subscript k comma m, T k m of z. Let us write it in the sequence in which the filtering occurs. The rightmost is Fm of z, that is the first filter that will operate on the input, followed by the channel C of z, followed by the analysis filter Hk of z. Okay. So, please remember that the sequence of operations is F filters first, followed by C, followed by H. Again, these can be switched around, does not matter, but the important thing to note is that the transfer function between the input and the output, okay. If wait, one second, I wrote the blue line wrong. Okay, the transfer function between input and output actually has to include these samplers as well. So, this Tk of z is actually these three filters downsampled by n. Okay. This is the result that we have just now derived. So, this is downsampled by, and you can check, you can multiply these filters out and check whether you get what sort of response. So, now the range for k comma m greater than or equal to 0, less than or equal to m minus 1. There is no n in this part because there are m inputs, there are m outputs, I have transfer functions between them. This matrix Tk comma m will be a m cross m matrix because m inputs can be related to the m outputs. So, if I were to capitalize on that, I can write an equivalent form in this fashion. Okay, this is T of z, this is a matrix, and this is a m cross m matrix. The inputs to these matrix are these inputs S naught of n all the way to Sm minus 1 of n, and the outputs are the S0 hat of n dot 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 Sm minus 1 hat of n. Input output relationship is given captured in terms of a matrix transfer function. You can think of it as a MIMO system between these. The reason this is very important and why this notation is very important is because we now, otherwise when you start writing the equations you get all sorts of messy expressions, but if you have a very compact notation like this, you can visualize, okay, at the end of the day this is going to be the 0th polyphase component of Hk of z, C of z, Fm of z, no problem. Some filter is there, I take its polyphase decomposition, take the 0th polyphase component, and then that becomes my transfer function. So, if you have this, if you are comfortable with this representation, then please follow along and say whether you are agreeable to this one. What does it mean if I write down the following condition? If T k m of z equal to 0 for k not equal to m. That means I get a diagonal matrix. Diagonal matrix means S naught hat depends only on S naught, Sm depends only on Sm, and so on. So, what have I eliminated? Inter subchannel interference eliminated. So, I have to design my filters such that T of Z comes out to be diagonal matrix. So, if this condition is satisfied, then there is no inter subchannel interference. Inter subchannel. Now, this is why this representation is useful for us, because the whole system can be simplified into a few very easily visualized conditions. No inter subchannel interference. Okay? You agree with that? Now,
can you also explain that how do you get the TKM or something? What happened to the upsampling by factor?
Okay. Yeah, no problem. I'll show that in a minute. So, when I have upsampling by n followed by filtering followed by downsampling, that is what is this theorem 4.1 of Yuan Pei-Lin.
That's the zeroth polyphase component.
Zeroth polyphase component.
So, here T's are polyphase components.
No. T is a transfer function. So, if you take one particular set of input output relationship, it is a Tk of Z, that is represented as Tkm of Z, which is given by the zeroth polyphase component of Hk of Z, C of Z, Fm of Z. If you combine, basically now you have all the inputs and all the outputs, you combine them, you will form an m by m matrix, all of which are obtained through this operation, correct. But for each of them it is a different, Hk will change or Fm will change. C of Z is there for all of them, because all of them pass through the same channel. Okay, now let us make a couple of more observations. Obviously, the ideal case would be if T of Z is equal to identity. If T of Z is identity, then actually we get a perfect recovery. If T of Z is equal to the identity matrix, this would be the perfect transmultiplexer or the perfect multi-channel carrier, multi-channel system. So, let us call it as the perfect symbol recovery. Whatever we transmitted, we received without any impairment. This would be the ideal scenario. Can we achieve it? But before that, let us look at one more element. After you have made this diagonal, what it then, see, supposing you have achieved the diagonal part, let us say this is T naught of Z, T1 of Z, T00 of Z, T11 of Z, the last one is Tm minus 1 comma m minus 1 of Z. Okay. Now, is the recovery of S naught from S naught hat from S naught, is it what is the input output relationship? It's as if S naught got filtered by T00 of Z. That is a filter. That means there is intra subchannel interference, because there is ISI present. Okay. So, basically if these are polynomials, if this is a polynomial, then there is no inter subchannel, but there is intra subchannel interference. That means ISI is present. Intra subchannel interference. Okay. Here is where the power of combining the signal processing and the communications come into play in a very nice way. I am going to now go back to the original formulation. Assuming that there is no inter subchannel interference is not the case. I am going to go back to this particular representation. So, which means that I have a matrix T of Z, m by m matrix, where each of the entries are T00 of Z, T01 of Z, all of those are matrices. I have m inputs, I have m outputs. Okay. This is another interpretation, again very important that you are comfortable with this as well. S naught of n all the way to Sm minus 1 of n, S naught hat of n, Sm minus 1 hat of n. input output relationship indicated by this M cross M matrix. Now T of Z is a matrix of polynomials, correct. Each of the entries of T of Z is a polynomial. Now if I take the 0th power, that is a constant term from each of those, I can write it and then group all the Z power minus 1 terms. I can write this as a polynomial of matrices. Okay. What do I mean by that? Summation k equal to j, let us assume j is the highest power of the polynomials that are present in T of Z. I can then write this as T subscript k, where T subscript k is a constant coefficient matrix times Z power minus k. Okay. So basically what did I do? Took all the 0th power terms of T of Z, all the Z power minus 1 terms, and then grouped them as matrices. So basically this becomes a polynomial of matrices. So in this sense, why is this an important way to represent it? Because I can now write S hat of n as a convolution. Very important that you now visualize this convolution. It is T naught, a matrix, times S of n, the input at this time instant, plus T subscript 1, that is all the powers of Z inverse that have been combined. Now what will this combine with? It will combine with not the current input vector, but it will correspond to the previous input vector. So that would be S of n minus 1, the previous input vector that was applied to the system, and so on. Okay. So basically this way of visualizing is also important. So if I were to give it some terminology, this is the vector, this is the vector or the block of data. Let me call this as the vector / block of data at time n, at time n. This is the block at time n minus 1, okay, and so on and so on. So if I now ask you to tell me how to eliminate inter-block interference, there is another term in multi-carrier systems where it says I want to eliminate inter-block interference. Okay. So inter-block interference, that means S of n should not have any dependent on S of n minus 1, inter-block interference. If I want to ensure that this condition is satisfied, it is sufficient that T of Z equal to T naught. No inter-block interference implies this T of Z cannot be a polynomial, it has to be a constant matrix, because under that condition, both these are by the way matrices, the T naught is a constant matrix, then there is, you are guaranteed that there is no inter-block interference. Inter-block interference. Okay. Now tell me what is the condition for no inter-block interference and no intra-block interference? T naught should be diagonal, that is it. T naught should be a diagonal constants, a constant matrix, yeah, basically. So that is what we are basically coming down to. So if T naught is diagonal, then we get no interblock or intrablock, or intrablock interference. Okay. So both these are interferences. Okay. Okay, very good. So this is where it has brought us. So I think we have started to develop some interesting tools. We have started to develop a good framework for what it is. So let me just end it with just the following important results.